Okay. Welcome everyone again. I'm gonna start with the introduction to today's CMS Policy Speaker Series. While we get in the next few minutes, we get more people joining in. Thank you everyone that has joined in today for this CMS Policy Speaker Series for the month of April. Today we're honored to have Dr. Oleg Demidov, that is the co-founder and the CEO of Carbon Space. He's joining from Barcelona, Spain, and also Dr. Ruslan Soravlev, who is the co-founder and the chief research officer at Carbon Space, and he's joining us from Dublin, Ireland. And there will be giving a talk on satellite powered technology to guide sustainability strategies in the food and forestry sector. So before moving to today's talk, as we always do, I just want to get your attention in a couple of announcements and upcoming events on our CMS program. You all know you can visit our website at carbon.nasa.gov. You're seeing there the homepage. There you can find information about the initiative, all of the funded CMS projects. We have almost 100 CMS projects that have been funded since the beginning of the CMS initiative. And you can find more information about our applications and stakeholder engagement efforts. Um, Important, we have a call for proposals from CMS that is open. You have the information there on the website. The deadline is September 30 of this year. And also important, we have our annual CMS science team meeting and the stakeholder workshop. And that's going to happen on September 27 to the 29 in the Washington, D.C. area. That's pending confirmation. So we hope that in the next couple of weeks, we'll send more information about that. I also wanted to take your attention in an upcoming RSET training that is relevant to this community. It is an introductory webinar on atmospheric CO2 and methane budgets to support the global stocktake. That's going to happen from May 11 to the 25, so next month. If you're interested, you can go visit NASA RSET and you can register for the training. Also, and relevant for this community, we recently had this workshop from this Applied Earth Observation Innovation Partnership that we have with the U.S. Forest Service. Today's talk is going to focus on applications on the forestry sector as well as the food sector. So I just wanted to call your attention in this workshop that we just had like 2 weeks ago with the U.S. Forest Service. And there are some key outcomes, especially around the topics of building communities of practice. So the website is there. I'll put the website on the chat. If you're interested, you can go there to the website and we'll have more information and a report from that workshop. And finally, we have this ongoing call for papers for a special issue of the journal Environmental Research Letters with a focus on carbon monitoring research and applications. The call is staying open at least until the end of this year. So if you're planning to draft a paper related to carbon monitoring or any related topic that you see there, please consider this a special issue. And now, with these announcements from the CMS initiative, I would like to formally introduce today's speakers, Dr. Oleg Demidov and Dr. Ruslan Suravlev. Dr. Demidov has over 15 years of experience in technology innovations and international business development, and he holds a PhD in satellite and inertial navigation and a master's in economics. And he's joining, as I mentioned, from Spain. And Dr. Soravlev is a former principal investigator in the GOSAT project. He has 15 years of experience in atmospheric science and holds a PhD in physics of atmosphere and hydrosphere. They will be presenting on their Ireland-based startup Carbon Space, and the efforts at providing a better carbon footprint estimation tool to the food and forestry sectors. So I'm going to stop sharing my screen and let Oleg share their screen. We will have at least like the last 15 minutes for a Q&A and discussion. So you're free to use the chat for any comments and questions to Oleg and Rosalind. So I'll leave you all with Oleg, and thank you all for joining.
Thank you, Dil, for this nice introduction. And yeah, welcome everyone. It's great that you are with us today. So yeah, let me start our presentation. So I am the CEO and co-founder of Carbon Space. And at Carbon Space, we are targeting to provide the carbon footprint transparency with the major focus on the land sector. And like briefly about our company, so we currently have about 20 people spread across, I think, 7 different countries, mostly in Europe, but also in Brazil and the USA. So we are backed by 2 leading VCs in AgTech in Europe, the Yield Lab and Rockstart. We have raised the seed round last year. And we are also so we have worked with a bunch of space players. So we have performed a case study for the European Space Agency, and so we have also created a bunch of peer-reviewed publications with regards to the approaches that we are using in our technology. So far, it have resulted in a number of projects, in commercial projects across, I think, 15 different countries on 4 continents. So mostly like in Europe and Americas. And we are targeting mostly medium to large size food producers, forestry operators. We're also working with the broad ecosystem of carbon offset players, and we are scaling quite nicely through these niches as carbon markets are growing. But what is really important is that we are trying to solve and fix a very important problem that the market have at the moment. So what we do is we are looking at how to make like much more scalable and cost-effective tools for carbon footprint tracking within the land sector. Because right now most of the tools are quite manual and slow and expensive. So in many cases you need to go on site to to measure the trees, understand their height, like canopy and so on, or you need to go to get soil samples, and then you need to get like additional like enough soil samples per hectare to be able to provide good enough estimations. And a lot of the data is self-reported in the land sector and is used for the assessment of like carbon footprints or like carbon sequestered in the within different ecosystems. And we can see that like there are no unified standards that can work in like any part of the world. And with all these issues, we can see that like the corporations cannot effectively report on their efforts on how they reduce the emissions, and because it's very difficult for them even to come up with a baseline of how much they emit within the supply chain. And at the same time, for carbon offset players, it's really difficult to provides the clear assessments of what the project is sequestering, and that's why like the whole market is like not moving with dynamics that it should move to basically help like move to like carbon neutrality and avoid like the progress of like global climate change. So we see our mission like as to provide much more scalable tools that are unified and can be applied to multiple different ecosystems. And so right now we have a bunch of solutions that we are providing to our customers and partners. So the first solution is the carbon map. We are providing the data on CO2 with regards to any country in the world. We are like implementing the resolution of 5 to 10 kilometers. We are providing the data for the last 20 years on the monthly basis. So this solution is good enough for the public sector, or if you want to understand the footprint on the level of region or like large municipalities. But then another module, which is carbon profile, is used when you want to go on the enterprise level, when you want to understand the footprint from particular fields and forests. Again, we are providing 20 years of data, of like monthly historical data with 30-meter resolution, which helps us to track the footprint for any areas above 1 hectare. So this is the major commercial product for us at the moment. And it is complemented by our carbon analytics module. So we are providing the dashboards that are showing the evolution of carbon footprint across time. We are helping companies to create the baselines, understand the trends, like around how their like land assets are performing. And we are also helping to understand the impact of the practices that are implemented on this land, like including like regenerative agriculture, low-till, no-till, cover crops, and at the same time, of course, if we're talking about offset projects, then it's about reforestation, deforestation, conservation, and all these different types of projects. So I think that was like very brief introduction about like what we do as a company on our products. And now I think it's time to say why we like can do it really nicely from the technology standpoint. And I want to hand it over to Ruslan to continue on like to continue our like talk about so how it works from the technology perspective. Ruslan?
Thank you, Oleg. Hello, everyone. So on this slide, you can see our technology core visualization. In our team, we use the two different approaches for estimation of the greenhouse gas fluxes and especially the carbon dioxide fluxes. So the first one on the left-hand side is a so-called top-down approach. And the top-down approach is based on the atmospheric greenhouse gas concentration measurements and inverse modeling to estimate the surface flux given observed fields of the atmospheric concentrations and wind speed, wind direction, and so advections. And so after that, we put it in some kind of the optimization process, which tried to minimize the difference between the modeled concentrations and observable concentrations. And due to this minimization, we can extract the surface carbon dioxide emissions. Right now, we try to reconstruct the emissions with the spatial resolution about 0.1 degree and monthly temporal resolution for the period of time since 2000 up to 2020. As a data source for this approach, we can use the satellite data for which measure the greenhouse gas concentration, like GOSAT, OCO2, OCO3, GOSAT2, Sentinel-5P, but Sentinel-5P has only methane data. But right now we're working with we have an experience to work with the GOSAT only for the carbon dioxide. But our system could utilize the other satellites data like the OCO2, OCO3. The problem will be with the amount of data because the OCO2 provide much higher, much bigger amount of the data, and yeah, there will be some computational tricks to utilize this. But anyway, we can use this data, and also we use the additional surface monitoring stations the data from the long time series from the station all around the world, like the global view or OPSPAC data. And this data allow us to stabilize the satellite data, because sometimes they have biases in these in the measurements, but the ground station allow us to estimate this bias and correct this bias during the assimilation process and in those problem solution. The other type of the approach is so-called bottom-up approach. Usually bottom-up approach uses the observation of the surface properties to resolve the carbon dioxide emissions, including using the emissions model based on the observation from the eddy covariance data, like the FluxNet station or MeriFlux data, and remote sensing data products. For example, in our case, we can use the data from the Landsat constellations, the Sentinel-2 data, and we grab the information from the bands, multispectral data from the bands of these satellites, and we create the model based on the machine learning algorithm, and we compare the features, the indices which we calculate from the remote sensing. We compare this with the eddy covariance data, and that's how can we train the model to reconstruct the behavior of the net ecosystem exchange on the ground. Depends on some features of the biomass feature or indices which we can calculate from the remote sensing. As a result, we can get the maps, monthly maps, with the resolution about the 30 meter that caused by the Landsat original resolution. So they're using the additional data like Sentinel with the 10 meter resolution will allow us to increase the effective resolution of this data, of the result data. So yeah, both of them have the advantages and disadvantages. For example, for the top-down approach, usually these results works well on the raw resolution, I mean the regional or country scale, and bottom-up approach usually works well on the high resolution with the localized solution, and have a problem with the extrapolating this model on the huge area, because they have aggregation error and so on. And thus the main idea, our main idea here, is to combine these two approach in something new, to force the local solution, I mean the high resolution bottom-up approach, be much more balanced and reproduce the observing concentration, carbon dioxide concentration growth rate. So that's how we can fill the gap of the mid resolution with the balanced value. So without aggregation error and with a much higher resolution than the raw resolution. I mean from the top-down approach. So that is the main idea, to combine two approach into one core, to grab the new quality of the data with the different resolutions, but with the balanced values, balanced with the observable concentrations. Next, please. So yeah, here is a sample of the results of our top-down approach. For example, two maps for the Denmark for the 2 different years, 2016 and 2019. It's annual values, fluxes of carbon dioxide, just for visualization how it looks like. And on the next slide, you can see the results of our bottom-up approach with a high resolution. So you can imagine that each pixel is about the 30 by 30 meter resolution. It's the same annual carbon dioxide flux. It's NEE, net ecosystem exchange, for carbon dioxide for the 4 different fields. So you can see that we can reconstruct some spatial variability inside the field. It's smooth, but we can see the variability in the sequestration for these fields. That's how it looks like right now as two different approaches on our side. So next, like you can say about few case studies.
Yep. Thank you, Ruslan. So yeah, let me continue on some case studies on how we actually use the data for different like commercial and sometimes non-commercial projects. So here is one of the examples of the cropland in North Dakota. We have performed it together with like one of our partners. And when we analyze the field, and in order to analyze the field, we just need to have the shapefile for this field and know the land cover of this for this particular field. So when we looked at the historical evolution of carbon data, we have found that like on average, this field was sequestering around like 5 tons per acre per year. And then we found that in the year 2020, this field like moved from like the green zone when it sequestered carbon to the red zone when it started emitting the carbon. So we didn't know what happened on this actual field, so what physically happened there. And that's why we start looking more deeply what happened. And we found that like if you compare 2 years, the year 2019 and the year 2020, then the behavior of the like typical like seasonal pattern was different. And we have found that like because of some problems, the fields just didn't sequester carbon as usual. And we found that this field, so when we checked with the partner, we found that this field was abandoned in 2020. So nothing was grown there. And that's why it was bare soil. Of course, the soil like did not sequester any carbon. And because of some like residues on the ground, it was actually emitting through the whole year. So this is how we can like very quickly see so if something is like happening on the field, if there is some like underperformance on the field, we can see it. And basically it applies to the vice versa case when, for example, some practice is implemented like cover crops or no-till, then we can see some additional uptake in carbon sequestration. And yeah, I think this one example, which is quite interesting. And another one is for the grazing land in Ireland. So when we looked at the evolution of the footprints, we found that this area is sequestering quite a lot of carbon. And then basically, as this is grazing land, then the grass that is growing there is taken out and it's used to feed cows. And then what we found is that so this land is quite significant carbon sink, but of course we just cannot say that all this carbon is sequestered in the soil, which is like really important to identify because there's much more permanent storage of carbon. And then what we did is we analyzed it together with our partner, and then we tried to come up with the quantification of soil carbon, just based on our data, and based on the data of which amount of carbon was taken was taken out from the field. And then we, together with a partner, quantified the amount of carbon that was taken through the harvest. And we found so this number with the partner. And then we quantified the number of tons of carbon that was sequestered by the land, by the field as the whole ecosystem. And then, so what is left is what actually stayed with the soil. So we found that 0.44 tons of carbon per hectare was sequestered by the soil. which is quite in line with industry averages for islands for this type of grazing land. And I think this is a very important aspect that we, like, in order to understand the carbon sequestered with the soil, we don't need to go to make all the soil samples. We just need to know like the net ecosystem exchange that we are measuring, and then we need to know the amount of carbon that was taken out from the field, and then we can come up with a good enough estimation of changes in the soil carbon. And another important implication here is that this carbon that was sequestered can be used to adjust the life cycle assessment for the particular production, and that was dairy production in islands. And then we found that if you take into account the amount of carbon that soil sequestered, then the numbers per like kilogram of fat and protein corrected milk like should be corrected as well. And what is important here is that so basically it's a good motivation to improve the grazing practices, like utilize more sustainable grazing, because it can actually reduce the negative impact of like livestock industry on the environment. Of course, it like doesn't mean that they can eliminate like the whole negative impact, but at least with this kind of assessment, they can understand that like if they take care of the soil better, then it can reduce some like negative impact that they have. And then, so what we can see is that, so the current practices are very tuned to the different parameters of the ecosystems that that historically could be measured in some nice way, and we can see that so most of the current standards and current protocols that are utilized in the industry, they are either targeting biomass estimations. So this applies to most of the cases when we're talking about forest or like agroforestry cases, when the wood biomass is the biggest part of the carbon storage. So then most of the current frameworks are focused on identifying above ground and sometimes below ground biomass. And then another part of frameworks are focused on identifying the soil carbon, and like trying to quantify the changes in the soil carbon to understand so how much carbon is left in the soil. And then at the same time, we see that, like again, from the standpoint of frameworks, there is a domain which is focused on the supply chains for food and forestry players. So we're talking mostly about GHG protocol here, or some guidelines of IPCC or ISO that are applicable here. And the second part is the nature-based solutions. So here we are talking about methodologies that are applicable to carbon offset markets. And then on this intersection, we are working on different case studies and methodologies that should be developed to give the market an opportunity to use more scalable tools like we have, for example. And then we are developing case studies with our partners on these different intersections. And I think there are a lot of interesting research and interesting benchmarking exercises that could be done here. And so basically we are, so we have a network of partners with whom we are working on this case studies and sometimes peer-reviewed publications. So we welcome everyone to like to discuss so what we can do together. So basically, if we can match any like current approaches with more satellite data with NE-based approaches. So we're happy to discuss collaborations here. So I think I will not jump into the details of like what can be done. So happy to address any questions on that front. And now I think I want to hand it over to Ruslan to talk more about science and technology aspects. Ruslan?
Thank you. So here is a list of the, let's say, challenges what our research team have right now. So some of them are prompted by a discussion with the customers. Some of them are caused by internal technological problem. But yeah, let's go through this. Through this list. First of all, we need to complete the combination of our top-down and bottom-up approach. So right now we have experience in this area from our case studies. So sometimes when we have huge areas to estimate, we can compare the natural fluxes from the top-down and the bottom-up approach, and that give us the understanding that it could be combined. But right now we are in process of this and of this combination, and waiting for some features what we can merge and grab the new data here. So the next is some time ago we decided to use another type of the model, so-called soil vegetation atmosphere transfer model, and as an additional model in our bottom-up approach. That because this model will give us the more understanding, more knowledge about the behavior on the ground, biomass behavior, and some additional parameters. But the problem is that these models are very sensitive to the input parameters, to the quality of the input parameters. They have a lot of internal hyperparameters which should be tuned, and usually the tuning process is very localized, so it's not so easy to scale this model from to extrapolate this model from one region to another. So, but again, if you have this tuning process and well-tuned model, our experiments show that it could be very useful tool because it's allowed to reconstruct not even the seasonal variation, but even diurnal variations. We have already set up some experiments for this model to understand the sensitivity of this model to the input parameters. That will give us understanding of how can we scale and by which parameters we can scale this model to other regions. So the next is some kind of the problem of our internal technology, because when up approach, when they use the remote sensing data, usually you have a problem with the clouds, and when you use the visual range or near infrared, you have a problem with the clouds. And if you have a clouds, you don't have the reflectance data, and that means you don't have the estimation of the fluxes. But we expect that the integration of the radar data, I mean the SAR data, for example, from the Sentinel-1, will overcome this problem. So it gives us the understanding of the biomass on the ground under the clouds, and that will allow us to fill the gap in our time series to get the full seasonal cycle for the specific area, for the specific fields, and so on. There are some problems with the radar data. The problem of integration this data into our current pipeline. But after review the publication, it looks like a solution for the cloud. But again, we need some retraining there and some additional model to use this data in our process. At the same time, we are trying to implement our bottom-up approach, based on the reflectance data for the methane data. But the problem here is that the eddy covariance data, which is a target of our training process, usually eddy covariance data for the methane places close to the wetlands or some specific type of croplands like the rice farms or something like this. And that gives us the limitation of the applicability of this process, of these models in the global scale. So that means as a first guess, we can use this model only for the limited number of the land cover types. If we use the IGBP classification, that means some crops and wetland mainly. But again, so we tried to implement the top-down approach, maybe somewhere as a further work. We will try to use the top-down approach for the methane because, for example, we have a Sentinel-5 data, which have a 5.5 per 7 kilometer as a new product. But again, so that will be a further work, and maybe that will give us the understanding again of a combined approach for the methane, for bottom-up and top-down approaches, and will give us the balanced value for the methane. So another problem for the bottom-up approach, our bottom-up approach when we use the eddy covariance data, if we look at the global distribution of the eddy covariance tower flux stations, we see that it's not uniformly distributed. So we have a white spot in the land where there are no any stations. For example, not so much station in the tropical area, but the tropical area is very important for the carbon dioxide, and you have a lot of clouds there. So that means sometimes you don't have the data from the remote sensing. And again, so not all the land cover classification types covered by the eddy covariance stations. And that means we can estimate where is the sensitive white spot, and maybe we can manage or maintain the eddy covariance station by ourselves with the partnership, for example, with the LICOR. And we can estimate, we can find the places where can we put the eddy covariance stations to solve the problem, to cover the gap, and to enrich our data sets for better understanding of the biomass behavior or land cover type behavior in the tropical area, for example. Another very important and very famous problem is how to separate the biospheric and anthropogenic emissions from the top-down approach. We cannot solve this problem right now in the correct way from the top-down approach because as a result, we have a total flux estimations. But one of the ways to do this is using the additional gas concentrations, gas types as a proxy. For example, air quality gases like the carbon monoxide, nitrogen oxides, or something else. That will allow us, if we assimilate this data together with the carbon dioxide, that could give us the understanding of the anthropogenic parts and the biospheric parts. I don't think so. I don't think that we will solve it in the global scale, but we can try to solve it in the local scale. For example, for the European part or Asia part or United States. So some closed domains, huge domains, but closed domains. Yeah, because in the global scale, yeah, it's pretty tough. And also one of the well-known question for the agri sector is, can you estimate the N2O fluxes from the agriculture, from the cropland, from the soil, and so on? Right now, we cannot do that, but we really want to. And the main problem here, what we see right now, is that not so much observation data about these components, and moreover, it's very localized data. So yeah, it's a difficult problem for us, but we're thinking about this problem because it's very, very important for the agro sector. Yeah, next, please, Alec. Yeah, and here are a few suggestions for collaboration, what we see from our side. First of all, our research part would be interested in participating in some internal workshops in the CMS because yeah, we have some research results on our side, and we would be happy to share them with the CMS to understand our problem, or maybe our activity on this side. Also, as Alex said, it's important to have a tool for monitoring, reporting, and verification. And here we can, the point where we can build some joint system for this problem for the agro sector, using the different satellites data and the observations data. And also, we would be interested in the data. I mean, the satellite data, for example, the access to the OCO2 and OCO3 products, L2 products, to use it in our top-down approach, and we can compare the difference between the results obtained from the GOSAT data and from OCO data in our technology, and understand the sensitivity to the difference of this data to these products. And that would be interesting results for us. And maybe we need to understand, maybe it would be an ensemble approach here. So when we have two different results, or results from different data source, and we can create some ensemble of this data to understand what the better, to grab the better solution. And as a result, we can take part or participate in some kind of intent comparison campaign on the reporting on the CMS side, on something like this. So it's a well-known inter-comparison way in the research part. So some papers about the inter-comparison campaign for different products. I mean, different results, L4 results. So global flux, carbon fluxes. And we would be happy to participate in this activity too. That's it from my side, I think. Thank you all.
Thank you.
And I think, thank you, Oleg, and thank you, Rosalind. And I think there is one more slide from your side, that is the contact information. Yes, so everyone that is here can have the contact information from Oleg and Carbon Space if they want to reach out. Thank you for those areas of collaboration slide. We will be more than happy. We were mentioning in the introduction that we have the CMS Science Team meeting and the stakeholder workshop coming up in Washington, D.C. late September. So we will be more than happy to engage you all in that effort and in many other activities that we're going to have throughout the year. But I want to we have several questions on the chat, and I want also to get Ben Poulter to join us in, if he can moderate this Q&A. Ben is part of, he's a physical scientist at NASA Goddard. He's part of our applications team and efforts. And he's also the one that has engaged with Carbon Space initially. So I want Ben, are you on?
Yeah, hi, Adil. Good afternoon, everyone, and yeah, thanks, Oleg and Ruslan for your presentation. So we have a lot of questions in the chat, and I'm sure there are other questions that people would like to ask. I mean, for me personally, it's really exciting to see what's taking place in the commercial sector using the greenhouse gas satellites, the remote sensing products in such a way that can be applicable to a wide variety of stakeholders. And I think there's a lot of interesting science questions that Ruslan you brought up in the last couple of slides, particularly with how do we use the greenhouse gas emissions to provide a service for looking at emissions and removals of greenhouse gases. So so thanks again. So let's move to the chat. Adil, unfortunately I joined a little bit late, so I'm not sure if I'm seeing all the questions. The first question I see is from Doria Gordon, asking about other greenhouse gases in addition to CO2. So are you looking at nitrous oxide and methane emissions?
That's the first question. Yeah.
Okay, great.
Yeah. So so not for the N2O right now. So we don't have anything to do this estimation for this gas. But for methane, we're starting some experiments for the high resolution. But but right now we have the limitation with the land cover types. Also, in the parallel, we have an experiments with the Sentinel-5P data from the methane as a top-down approach, but on the much coarser resolution, so about the 3 kilometer resolution and so on. But it's under development right now, so we are trying to build some experiments. We have some results, but we try to stabilize this data because again, you don't have the data. Sometimes you have gaps in the data. You need to understand how to overcome this.
And yeah, we know for sure that some satellite missions are coming that will add more methane data to the table. So yeah, really interesting to look at like what is coming and see how we can use it, and yeah, maybe we can provide a better temperature, better solution than we can do right now.
Thanks. Doria, did you want to follow up on that? If not, we can go to the question from
no, thanks, that's fine, appreciate it.
All right. Okay, so next is from Ying Sun. Yeah, how does one go about accessing the data products, and sort of what is the characteristics of the formats that they come in from a spatial resolution point of view?
Ruslan, do you want to take this one?
How to access the data products?
Yes.
I don't know, Alec. I think it's for you a question.
Okay.
Are they available?
Yeah.
Or
yeah, let me.
Okay. Yeah. Maybe it comes. I mean, it might be a bit about the business model. I mean, I think it's a sort of a unique. Well, compared to sort of how we work at NASA with free data. Sort of how do things work with your business model?
Mm-hmm. Yeah, so basically the global carbon map that we have with the low resolution, so can be accessed through our website. So we have a special page where you can look at the map, and then so basically you can see the data for different countries. So you can see it for the last 20 years, and then you can also see so how the picture of colors changes depending on the level of the emissions or uptakes on the map. But then so we are also providing the access to commercial customers who wants to look at a specific region, for example, within some country or multiple regions in different countries. So for this we have special pricing, and the price depends on the area size. So this is about the low resolution, and then with regard to the high resolution, so we usually need the shape files from the customers and the knowledge about the land use type. And then with this knowledge, we like processing the data, and we are providing the access to a personal account where the customer can see the data for different regions and for different like land assets. So this is the data on the monthly basis, and yeah, here we are providing it also on the commercial basis. Yeah, the pricing depends on the like number of land areas, on the total size of the areas. So yeah, in general, so we are talking about your pricing based on the size of the project. Yeah, and depending on like the number of land areas, so the pricing is also a bit different. Yeah, I would say our target is yeah, to probably try to reach like for like for most of the projects around like €1 per hectare per year, if we're talking about like quite large projects. So yeah, I think that's a kind of pricing that like will be able to help the whole like carbon offset markets to grow and like spending much less on monitoring and much more on the actual climate actions.
Okay, thanks, Oleg. Next question is from Ralph Kahn about the sort of the integration of the bottom-up and the top-down approaches, and whether there's an optimal spatial resolution that you work at to produce the sort of the high-quality estimates of the carbon flux maps. And so I guess, yeah, thinking about this from the OCO2 GOSAT type resolution for the CO2 retrievals, and sort of how do you disaggregate that to the information that the stakeholders are interested in that might be at a Landsat or sort of MODIS-based spatial scale. So yeah, is there sort of an optimal spatial resolution that you've identified there?
Well, I think the short answer will be no, we don't find the optimal spatial resolution, but it's some kind of the tricky question, because the answer depends on the specific region, because top-down has its own uncertainty, and this uncertainty has a two-dimensional distribution. So it's a map of the uncertainty distribution, and the value of this uncertainty depends on the data availability in this region. For example, if we don't have enough data in the tropical region, again, we have a huge posterior uncertainty there. And the main problem here is how to work with these uncertainties on the top-down level and the bottom-up level. So, of course, if you have some kind of the homogeneous surface, I mean the land cover type, you can work with the high resolution, with the balanced values, with the high resolution, spatial resolution. But in case of you don't, so you have some, I don't know, savannas with the forests in the small region. So it's not so easy to work with the high resolution. I mean, to combine these two approaches, it's better to rely on the high resolution. But yeah, so it's not so straightforward right now. We are trying, during our case studies, we're trying to find these features. How can we combine this, and when we can combine this? That's what we do right now. So we have some positive experiments. So success in experiments. We have some so results. We try to find the features. How can we combine, and what it will give us as a result.
So, okay, thank you. Next question is from me. So along the same lines as Ralph's question, I think, which is getting at the uncertainties, are your stakeholders interested in monitoring the year-to-year changes in carbon sequestration, and sort of how do those requirements or demands get put in the context of the uncertainties? And so, your uncertainties are obviously going to be different based on what sort of management practices and biome you're working across. but it's also going to affect sort of the efficient or the effectiveness of how you monitor carbon sequestration year to year or at decadal timescales. So I was wondering sort of, what is sort of the reporting requirement that you're working toward in terms of annual or sort of decadal scale monitoring?
Yeah, I can probably start. So I think right now the standards in the sector is like annual data. Sometimes it's even biannual data if we're talking about some like large offset projects. But I think with our data, it's possible to go to the monthly basis, which is not that important for the reporting at the moment. So annual data is good enough. But then using monthly data, sometimes you can identify important changes in the practices, and you can compare kind of baseline scenarios against what is actually happening. So it helps to understand some, identify some early alarms that will show that something needs to be done. And then on the level of uncertainties, Ruslan, do you want to add here something on that front?
Not so much, but so basically it depends on the specific case study. So yeah, not something what we can postulate that it is this practice and so on. So we just can, sometimes we can just say to customer that we have some suspect region in our data time series, and then the customer said, okay, yes, we have done something there with our fields, as you see in the case study in the presentation which Alex showed. So yeah, it's usually right now it's basically a case study, from case study to case study.
Great. We have 2 more minutes. Question from Ying Sun: are there sufficient local data, especially in developing countries, to calibrate parameters in SVAT?
I don't think so. And that's why we did some, first, what we did at first, it's some kind of the sensitivity tests for the SWAT models to the input parameters and hyperparameters, because we are relying on the some kind of assimilation process. Maybe if we can assimilate something, some global data, I mean external data, for example, weather data or remote sensing data, we can assimilate this data and tune the parameters in the SWAT model, hyperparameters in the SWAT model. That's what we try to understand by the sensitivity tests. Can we tune these parameters, hyperparameters inside the model without any localized data from some external data?
Great, thanks. And we can get to the last question from Joe Rudak. From this data, do you have any insights into whether agriculture is resulting in carbon losses or sequestration? Production agriculture is resulting in carbon losses or sequestration?
Yeah, I think it really depends on the region and the country. So of course, in tropical areas, we have a lot of deforestation associated with, especially livestock production. So I think here the impact is quite negative. But then if you look at the countries like Denmark, so we have a lot of projects there. Then yeah, in many cases we're talking about very sustainable production. So if it is plant-based, that's sometimes those practices that are implemented provides a positive impact. So I think it's very important to look at specific practices that can be implemented in specific places to be able to make sure that these activities are helping planet and not destroying it. But yeah, of course, we need to go like a very long route until we understand all the specifics and can monitor and implement all the actions.
Thank you, Oleg and Rosalind, and thank you, Ben, for engaging with Oleg and Rosalind, and for your time. We have the Ben provided the link to the IPCC working group, the third working group report that was released this afternoon. I want to, because we still have some people. It is 1 p.m. If there is someone that wants to make a question or comment to Oleg or Rosalind, we have 1 minute now. Is there anyone with a question? Okay, if not, you have the contact information of myself. You have the contact information from Oleg. We had a great discussion today. Thank you, Oleg and Rosalind, from joining from Europe. Thank you, Ben. And as I mentioned, we will archive today's recording and the slides in the CMS website. So thank you again for everyone for joining, and especially thank you to Oleg and to Rosalind.
Thank you, Adil. Thank you, Ben, for organizing. Thanks, everyone.
Bye.
Thank you.
Bye.